Okay, so we can start. So we'll pick up on chapter 6 where we left off last lecture. Before we do that, I just wanted to mention one thing. So when I looked at the tests, and probably most of the students that are in class didn't do this, but I'm pretty sure the students who are not in class did what I'm going to give an example of, and that is, I'll look at the examination and there won't be any derivation on it. It's just basically random guessing at the answers. You have to try to derive the solution before you answer any multiple choice. So if you ended up getting 50% by that approach on the first exam and the retake, I can almost guarantee you're going to get less than that, 50% on the multiple choice on the second exam. So next exam, make sure you simulate a test environment where you reproduce, you derive the solutions. And so I already mentioned the first thing you should do when you start any problem is you should draw a cartoon. The next thing you should do is apply energy balance. Now we're moving on to chapter 6 and 7 and 8 where we're going to have to do entropy balance. So if you're not comfortable drawing a schematic and doing energy balance, you're going to really be uncomfortable doing entropy balance. So really the class gets hard at this point on. So make sure if you don't know how to write out energy balance, right, or do it for every problem, then you need to practice that. Okay, so let's go to this. We're dealing with heat pumps, heat engines, and refrigerators, and later on we'll talk about perpetual motion machines. And so this is just an example of a system where I have a heat engine, and it consists of 4 subsystems, and we put work in to pump the fluid, evaporator to turn water into steam, steam through a turbine, reduce the energy, right, the enthalpy of the steam to a lower enthalpy, say of a lower energy steam or saturated vapor, right? And then we get work out. Here we have a saturated vapor. The pump only works. Pumps don't work on pumping vapors very well. They're more efficient on pumping liquids. So we condense all the vapor to a liquid and then pump through the process. And then here's an example of our P or T bell curve. And state 1 is after the pump, increase the pressure, right? So you can get flow. And then through the evaporator, you go from saturated liquid to steam. Through the turbine, you go from steam, superheated steam, to another type of steam. Of course, 3 could be anywhere down here or within here, but I just put it out here, so now I still have superheated steam. Then the condenser converts all the steam to liquid, and then the pump brings it back up again. And so there's an area in this curve, of course, and if I look at it, it's clockwise, right? So work by the system. Okay, so work into the pump, work out by the turbine, heat in to the evaporator, say from a volcano, right? Constant source of heat, nuclear reactor, whatever it might be. Heat out, the condenser has to suck heat out, say to the ocean. So this power plant, right? Very general schematic of a power plant. So state of the art related to a PowerPoint, if you're a civil or environmental engineer, is that they're rejecting the heat from the power plant to a large body of water, say the coastal shoreline. Well, you're rejecting heat to the coastal shoreline, you're increasing the temperature, you're killing all the aquatic stuff, right? Coral reefs are, so they have to find a different way. So state of the art related to civil or environmental engineering is making more efficient systems so you're not increasing the temperature of the coastal waters from your power plant that's along the shore. So there's a lot of money that's being invested, being put in by the Department of Energy on overcoming this coastal shore water heating. But anyways, you still need to reject the heat somewhere. So there was this Kelvin-Planck statement, which we're going to get to. You have to add heat and reject heat. You can't have a cycle that operates by purely adding or just purely removing heat. You have to have a sink and a source. Nevertheless, okay, so we have this. So let's just go up to here. And first law, I can use the first law and I can get the net work out equals Q in minus Q out. And do energy balance because it's a cycle system. The change in internal energy of my system for a cycle is equal to 0. And so I can also do this work net out. Well, work net out is just work out minus work in. So if work net out is negative, that means I have more work in than work out. And then when I write out, I can write out the full energy balance, and I can replace work out minus work in with work net out. And because delta E is equal to 0, I end up getting work net out is equal to the heat in from my volcano to heat out towards my ocean, right? Large body of water. And so the heat engine, its total net work out is going to be dictated by, so of course I can put more heat in if I'm next to a volcano versus the engine of a motorcycle, right? And I can suck more heat out if I'm using an ocean relative to my bathtub, right? Now of course the motorcycle engine doesn't really act as a reservoir, it's too small, but a volcano would. And the bathtub, okay, if I have a micro cooler the size of my thumb, then the bathtub probably works as a thermal energy sink. But to a power plant, the bathtub doesn't work at all, right, for a sink. So let's introduce some new symbols. So let's use QH, QL, TH, and TL. So just instead of high temperature and low temperature sink and source, I'll just use this. So I have my reservoir source, at TH, which is rejecting heat, QH, and then I have my reservoir sink at TL, which is sucking heat, QL, from my system, which is a heat engine, which represented here kind of represents what I had above: pump, evaporator, turbine, condenser, working in a cycle, and I get some net work out. So related to this, I can calculate a thermal efficiency. So the thermal efficiency is going to be the useful energy out, right? Or work net out versus the useful energy in. Or, well, since I did this work net out, then I just have the energy in, which is QH. And so I can rewrite this in terms of QL and QH as such for the thermal efficiency. So for this to work, of course, TH has to be greater than TL. Right? So if TL is is a higher temperature than TH, how am I going to get heat to go in this direction and get work out? So coupled with this is also QH has to be greater than QL. And so before I had this work net out, which is equal to Q in minus Q out, which is QH minus QL. So in order for me to have work net out, QH has to be greater than QL. In order for QH to be greater than QL, I have to have TH greater than TL. Okay, so these are just requirements, right? These must hold. So both of those must hold. So what are the ramifications if is less than QL, or QH dot is less than QL dot. So just a question. So what happens if QH is less than QL? Just look at one of the expressions. Of course, I could put dots above any of these, right? So if work net out, that's the total work out. I could put a dot above it. The power out, right? The net power out. If I put W dot. So what are the ramifications to the thermal efficiency if QH is less than QL? I have a negative thermal efficiency, right? So it can't happen, right? And the same would apply here. So QH has to be greater than QL because we already know the thermal efficiency is defined to be a number between 0 and 1, where 0 represents 0% and 1 represents 100%, right? And thermal efficiency is one thing. There's an overall efficiency, right? So related to this thermal efficiency, just a quick question. So if I want to make the thermal efficiency, so work net out is definitely the useful energy out, right? Work net out, that's the useful stuff out. So if I want to make it a total efficiency, what would I replace QH with?
Energy. Total energy.
Total energy in, right? So that would be, in this case, if I put in some here, right? And plus QH would be my total efficiency. So I'd have whatever other energy I put into the system. But in terms of thermal efficiency, all I have to do is, and I already know that Q out net was equal to QH minus QL. So I'm just using heats in it. Okay. So let's go back to the refrigerator pump. And so a refrigerator is a device that transfers heat from TL to TH. Okay? So now I have my condenser up here. I have my compressor. I have an evaporator. And I have some expansion valve. So my condenser rejects heat to a high temperature source or sink. And my evaporator sucks in heat from a lower temperature. So this is a source, high temperature. You can look at them as both source and sinks, but anyways, usually the high temperature is the source, but we're going to reject to a sink, and we have here a low temperature source. And I can put numbers here. Okay, so what would be a low temperature source for a refrigerator? What would be an example? Inside the refrigerator, so what would be something inside? Food. So I can put a T-bone steak, right? So I'm taking heat out of my steak. It's getting sucked out because the evaporator, in order to take a fluid, right, and increase its energy, right, on the bell curve, to go from liquid to a superheated. No, really, that was with the turbine. Here, I'm not going to be going to superheated. I could just be going to a saturated liquid. Then I have an expansion valve, and I condense it, compressor. So if you open up your refrigerator or you open up an air conditioner, it has a very similar type of subsystem. So in terms of refrigerators and air conditioners, you always hear this is the part that usually goes bad first, the compressor, and when it starts making really loud knocking noises, your compressor isn't working properly. So let's put just some temperatures and pressures associated with it. So here I'll have some P1, T1, and P2, T2, P3, T3, P4, T4. And I should point out one thing I forgot to do here is I forgot to put the compressor consumed, so there's some work in. And it's net. Typically it's only work input, but I put net here anyways. In some refrigerators you'll also have a pump systems, but in general you only need these 4 subsystems for your heat pump or refrigerator. So let's just put some realistic numbers associated with each one of these. So P1, say 800 kilopascals, 30 degrees C, or 303 Kelvin. P2, 120 kilopascals. So 120 kilopascals corresponds to what at sea level? How many atmospheres is this?
Was it 100? Was it like 101?
Yeah, so it's 101.1, right? Kilopascals equals 1 atmosphere. So anyways, so at this stage here, before the evaporator, I'm getting it close to atmospheric pressure. So 120 kilopascals, but I'm using, in a refrigerator, you don't use water necessarily, you use a refrigerant. And so it's at minus 25 degrees C, or 248 Kelvin. And then I'm at 0.3, I'm an evaporator, so evaporator increases the enthalpy of my working fluid. So I stay at 120 kilopascals, but I change it from a liquid to a vapor, still at 25 degrees C, or 248 Kelvin. So let's put just a little, so right here I have saturated liquid, right? Here I have saturated vapor, compressor. Now I'm compressing it, so I bring it back to 800 kilopascals. And in that process, I increase the temperature to 60 degrees C, so 333 Kelvin. So saturated vapor, what is it here?
Saturated vapor. Maybe a mixture.
It can be it's usually a mixture, right? But it's still, it's not a pure liquid because you have to condense it. But the best way to do this is you end up picking what refrigerant's in there, and then you can look at, and so when your technician comes out, they might be checking the pressure of your system. They're usually measuring the pressure at the aft end after the compressor. If the pressure isn't high enough, So of course, if it isn't the right phase at that point, it's not going to be at the right pressure. So if you have a leak or you don't have as much fluid, but they typically, when a serviceman comes out and checks the operation of your air conditioner or your refrigerator, whatever it might be, they're going to be checking the pressure at process step 4. Okay, so related to this, P1 is greater than P2, T1 is greater than T2 for the expansion valve. And then I can use the ideal gas law. Of course, my system might not be working over pressures and temperature ranges where my refrigerant behaves like an ideal gas, but you can still use the relationship to get some ideas. So I can use this relationship, PV, this is big V, so I have M, R gas, T, so I can get a volume, R gas, T over P, and then I can get, I'll just put a subscript there, G, T1, P1, now this is a small v, V2, RG, T2, P2. And so if I want to look at this, I can just put in numbers, RG 303 over 800, RG 248 over 120, and if I look at this, this ends up being 0.379 RG, and this is 2.07 RG, and based off these numbers, V2 is greater than V1. Okay, I'm just going through numbers where I can get approximate values using the ideal gas law and my gas constant. So if I look in the appendix or I look in the book, I can pick a fluid and it's going to tell me its or gas, and it's going to tell me its corresponding gas constant. So there's a gas constant for air, gas constant for steam, gas constant for oxygen, molecular oxygen, whatnot. So let's do the compact version of the same thing. So I have my refrigerator heat pump in a compact schematic, and now I just have TH, TL, QL, QH, work net, in. So if QL is greater than QH, then we already know that the thermal efficiency 1 minus QL over QH. QL is greater than QH. QL is greater than QH. So this is greater than 1. So this ends up being less than 1.
Would be less than 0.
Well, yeah, less than 0. So it doesn't look good. And all this is basically saying is we're never going to be able to pull more heat out of our steak, no matter how much work we put in, than we can reject to our house. We're always going to have to reject more heat to the house than we can pull out of our steak, no matter how much work we put in. Of course, for a refrigerator, we want to cool the steak at a minimum amount of electric power input, right? Or we want to cool our house with the air conditioner, right? With the minimum amount of electricity going to our air conditioner. Now, the condenser part in your traditional, that's located in the vents within your house. So they have this long tubing that comes in with the cool liquid, right? compressed liquid, and then that's having the condenser, your air comes across it, and you're rejecting heat from your condenser. Okay. So just some quick differences between a refrigerator and a heat pump. So a refrigerator maintains QL at a constant temperature by removing QL. And a heat pump maintains TH at constant temperature by transferring QH heat. So the refrigerator, right, takes heat, right, tries to keep my steak at TL by removing QL heat. My heat pump tries to heat my house, right? Keep my house or keep my whatever it might be at a higher temperature by adding so much heat. So one's keeping something at a low temperature, one's trying to keep something at a high temperature. Okay, so one thing I wanna just introduce some new terms, and they're called the coefficient of performance. So if you end up working for a company that manufactures devices that relate to heat transfer, then the coefficient of performance is going to be very important. Of course, okay, so if I say you work for a company that deals with heat transfer, well, basically what we've learned from thermodynamics that everything deals with heat transfer. But in some cases you might be working, well, now they have computers where they have heat pipes within that cool the chips. So if you're going to design new computers, right, that operate really fast, right, they need to stay cool, the processing chips need to stay cool, so then you're going to be working with somebody who provides heat pipes that have a large coefficient of performance. So there's actually some little circulatory condenser evaporator pipe system that cools the CPU or the GPU in computers. So if you're working with a company, they're going to be, and you're ordering the parts from them, you're going to be asking them what the coefficient of performance of your heat pipe is. So the coefficient of performance is defined to be greater than 0. So, and then I'll just write what I kind of said in words. As an engineer, you will use / hear about this term, i.e. COP, a lot. Okay, in this class, we're not going to do that much with calculations related to the coefficient of performance because it's more important that you are able to define QH, QL, and you're able to do thermodynamic processes to define the amount of heat that's being rejected or added within some subsystem. And then you can always go to, once you do that, then you can plug in QH, QL, work in, whatnot, to calculate the coefficient of performance. So just like the thermal efficiency, you know QH and QL, you can calculate the thermal efficiency. The hard part was calculating what QH and QL is. But to plug it into that expression is pretty simple. So we'll just go over what they mean. And so you'll be using this a lot because heat pumps and refrigerators are used So I just used the example of a computer, and there's a heat pipe within it. So your high temperature source is your computer chip. There's some fluid that runs by it. It evaporates. You have to condense. The condensing rejects through fins and whatnot to the rest of the room. and there's a coefficient of performance associated with it, there's a thermal efficiency associated with it, there's a total efficiency associated with it. So in aircraft, another example, so if you have a high-speed aircraft, the fuel is used as a coolant in addition to a combustion. So, but also to that, in the cockpit, there's a bunch of other things that they need to cool and whatnot, right? Electronics and all this other stuff. So you always have some type of heat pump or refrigerator in almost all technologies. Okay, back to the coefficient of performance. So in terms of coefficient of performance, it can be broken down into two parts, one associated with the refrigeration system and one associated with the heat pump. Now remember, the refrigerator maintains your temperature at a low temperature, right? And then the heat pump maintains something at a higher temperature. So coefficient of performance is of a refrigerator is defined to be QL over work net in, where work net in is work in minus work out, or QH minus QL. So the coefficient of performance of my refrigerator, I can rewrite it as QL over QH minus QL, which is 1 over QH QL minus 1. So QH always has to be greater than QL. So this number is, this still applies, QH greater than QL, so this number is always going to be a positive number. If QH is really large relative to this, then I'm dividing by some. That means ideally I want this to be as close to 1 as possible. And then when this is close to 1 as possible, this ends up being a very small number. My coefficient of performance of my refrigeration system is a large number. So coefficient of performance has to be greater than 0, but it can be greater than 1. So it kind of gets confusing. So you'll see coefficient of performance of 100, you'll see coefficient of performance of 10 when you're dealing with different systems. So it can be greater than unity, unlike the thermal efficiency. So for the heat pump, now I'm keeping something at high temperature, right, with QH heat. So now instead of QL, I have a QH. So my coefficient of performance of my heat pump is defined to be QH over work net in. And of course, work net in is still the same, work in minus work out, QH minus QL. And then I just replace this around, so I got QH minus QL. And then I can rewrite it as 1 over 1 minus QL over QH. QH still has to be greater than QL, right? So then when they're close to 1, that means this gets small and my coefficient of performance of my heat pump is much greater than 1. So the same applies. So P of my heat pump must be greater than unity. And I can relate the coefficient of performance of a heat pump to the coefficient of performance of a refrigerator. So the coefficient of performance of my refrigerator has to be greater than 0. For a heat pump, it has to be greater than 1.